0.055 kilograms times meters per second. For the peak of hill 2, we have 0.068 times 0.2 over 0.82, which equals 0.017 kilograms times meters per second. For the decline momentum of hill 2, we have 0.068 times 0.15 over 0.48, which equals 0.021 kilograms times meters per second. For hill 3, uphill, we have 0.068 times 0.12 over 0.23, which equals 0.035 kilograms times meters per second. For the peak, we have 0.068 times 0.36 over 0.79. This equals 0.031 kilograms times meters per second. So for hill 3, momentum down, we have 0.068 times 0.13 divided by 0.23, which equals 0.038 kilograms times meters per second. For 12, we have change in kinetic energy equals W net. We're supposed to find when the tallest hill reaches a flat track, calculate the distance till the cart will stop. Okay. So this turns into KE final minus KE initial, which equals force times distance. And then we have 1/2 mass times velocity squared final minus 1/2 mass times velocity squared initial equals mass times 9.81 times mu times distance times cosine of theta. You break that down into 1/2 mass times distance divided by time squared final minus 1/2 mass times distance divided by time squared initial, which equals mass times 9.81 times mu times distance times cosine of theta. Normally in this step we would break down the mu again, but we calculated the mu earlier in a different question, so why break down mu when we already have it? So now you break it down into taking out the initial kinetic energy, because the final minus the initial is just redundant. So filling it in, you have 1/2 times 0.068 mass of the ball times the distance divided by time, which is 0.13 over 0.23 squared final equals 0.068 times 9.81 times 105.89 times 0.13 times cosine 142.7, which we got that by subtracting the angle by 180. So you come out to get 0.0109 on the left equals negative 7.32 on the right. And so you get kinetic energy equals 7.5308. So ultimately it'll take about 8 meters to stop. So for 13, on this page, we are finding the impulse momentum theorem. So force times change in time equals change in momentum. But the easier solution to this equation is simply power down minus power up. So for hill 1, we have 0.022 minus 0.034, which equals negative 0.012. For hill 2, we have 0.021 minus 0.028, which equals negative 0.007. And for hill 3, we have 0.038 minus 0.035, which equals 0.003. For 14, we were supposed to calculate the minimum acceleration, force, momentum, kinetic energy, work, power, and potential energy of gravity needed to complete the loop. But since my loop is before my start, or is right after my starting mechanism, I cannot calculate because I do not have the proper measurements to do the calculations. So we'll move on to number 15. Calculating the centripetal acceleration of the object completing the loop. So you have centripetal acceleration equals tangential speed square over the radius. Tangential speed square can be broken down into pi radius squared over radius. So I have pi 0.16 squared over 0.16. So the centripetal acceleration equals 0.5027 meters per second squared. So 16, we are finding the centripetal force of the moving object completing the loop. So this one's just Fc equals mass times tangential speed squared divided by radius. So we can just use what we got in the previous question. So 0.068 for mass times the tangential speed squared divided by radius is 0.5027, which comes out to equal 0.0342 newtons. For 17, we are finding torque coming off of each hill and the loop. So torque equals force times distance times sine of theta, which equals torque equals mass times 9.81 times distance times sine of theta. For my loop, I have 0.068 times 9.81 times 0.32 times sine 45.7 equals 0.1528 newtons meters. For hill 1, up, I have 0.068 times 9.81 times 0.1 times sine 13.1, which equals 0.0151 units meters. For hill 1 down, we have 0.068 times 9.81 times 1 times sine 141.5, which equals 0.0415 newtons meters. For hill 2, up, we have 0.068 times 9.81 times 0.2 times sine 18.8, which equals 0.043 newtons meters. Down for hill 2, torque, we have 0.068 times 9.81 times 0.15 times sine 158.8, which equals 0.0362 newtons meters. For hill 3, up torque, we have 0.068 times 9.81 times 0.36 times sine 83.5, which equals 0.2386 newtons meters. So for torque down of hill 3, we have 0.068 times 9.81 times 0.13 times sine 142.7, which equals 0.0526 newtons meters. For 18, we're finding the mechanical advantage of our hills. My hills suck.